the Department of Computer Science of the University of Leuven. He holds a research professorship and is one of the founders of the field of statistical relational artificial intelligence. So we are very happy that he's here. So I welcome Luc to give his talk.
Okay, so thanks a lot for having me and for the kind introduction and the opportunity to present our work here. So I'll be talking about probabilistic logic programming, which is like, in the context of statistical relational learning, a kind of good combination with a programming language as a background, and then also like adding probabilities on top of that. So this work fits two frameworks. There is the statistical relational AI because it's using logic, first order logic, relational logic, but it's also fitting the probabilistic programming paradigm because it's really a programming language that you can use to program. And so, yeah, in that regard, I would argue it has the best of both worlds, potentially. I should stress this is work with especially Angelika Kimmich. I've given this tutorial a number of times, or many times, often together with her. She made a lot of the slides here. Also, other people like Guy van den Broek contributed slides, or parts of slides. What you'll see is also that there's a very big bunch of them. I think there's like 500 slides or something. If you look at the slideshow, almost 300 in total. I'm not going to see everything, obviously. The reason is that I guess some of the stuff was already seen yesterday. Some things will be seen tomorrow. And so I'm going to try to focus dynamically on, well, what is not covered in these other parts. Okay, so I guess you've seen this. The key question that statistical relational AI is trying to tackle is combining three elements. There is reasoning with relational data, there is dealing with uncertainty, and there is machine learning. And you find that back in different subfields of AI. Learning, of course, in machine learning. Uncertainty reasoning, well, there is dedicated conferences on that. What is very well known is probabilistic graphical models. And then on the reasoning with relational data, there is logic, there is databases, but there's also like logic programming, and we very much play that kind of card. The field is known under these different names. As I said, one distinction is really that people in statistical relational AI, they focus often on the relational part. They don't care so much about probability, they don't care so much about programming, whereas people in the programming language community, and I'll give some examples of that, they're really playing the programming language card, and they come up with other types of formalisms. They just take a programming language and put some probabilistic primitives on top of that and do things that are in spirit very, very similar to what statistical relational AI is doing. It's just different fields, but here it is combined in a sense. Some of the kind of motivations for our work come from a number of applications, and I'm just going to go through some of the things that we've done in the lab at Leuven in the past 10, 15 years. One of the motivations for the probabilistic logic programming language Problog that I will be talking about most of the time is this one. It's kind of a probabilistic database. It's basically the BioMine database that my colleague Hannu Toivonen produced in Helsinki. And he did it by crawling the web public databases. And you get things in there like pathways, genes, locus, phenotypes, proteins, and stuff like that. But given that the information was scrolled on the web, the information that you find is kind of uncertain. So if you zoom in on the network, you'll see things like nodes being particular genes in a particular database. You'll see like biological processes in the gene ontology. But then there will be these relationships. But the relationships, given that they're kind of never entirely certain, you can associate to them a kind of degree of belief. How much do you believe that this relationship holds? And then what you essentially get is a probabilistic graph, a probabilistic network, which you can directly represent as a probabilistic database. And that will be a source of inspiration for a lot of the stuff that comes afterwards. We've been using that in a lot of applications. One of the applications that we've been looking at is in biology, where you can try to analyze data like coming from microarrays and then interpret that in the context of pathways. What people were interested in is like finding the kind of explanations as to why these phenotypes correspond to particular mutations in a sense. So reasoning about that, and that is some of the things we've done with that. Other examples that are very inspiring, I think, is the NEL, the Never-Ending Language Learning story from Carnegie Mellon. You'll have William Cohen next week, I think. He's coming for ILP. And he's been doing great work together with Tom Mitchell and many others. What they've basically done is like they crawl the web, and they are actually extracting from web pages these kind of facts. But given that you again extract them with natural language processing techniques and with kind of machine learning techniques, you're never entirely certain that what you find holds. And so again, you can kind of associate, well, a kind of degree of belief, a certainty factor, a confidence, or whatever. And that can be interpreted as a kind of probability that you can use. Today, people are using knowledge graphs, which are very much in the same spirit, and with adding probabilities, you add extra power for reasoning and for learning. Some of the things that my student did, my former student Ingo and Niels, was look at games in this massive multiplayer online games. And what you have there is very much a relational setting, because if you look at the state in one of these games at one point in time, you get something like a kind of network, a kind of graph. I mean, there will be players in there. There will be alliances, there will be cities, there will be armies, there will be resources. These will all be the entities in the kind of graph. And then there will be relationships. Maybe a player owns a resource, maybe two players form an alliance, and things like that. And so what you would ideally like to do, if you build AI systems that are able to play these kind of games and to adapt also to users, then you would basically like to make models that will tell you how the world will evolve, basically. So you've got past data, like these snapshots, these graphs, these evolving graphs, and ultimately what you would like to get is kind of models that will tell you how likely it is that in the next point in time, maybe well, some player will attack you, and if you're able to do that, maybe you can take better actions, actually. You can look at tracking over time. You can track objects. You can track people over time. It's again very much relational. If you look at a reception in a kind of event like that, you'll see that people come together. Some people will leave the group at a certain point in time, and again, you can try to reason about that in order to predict what's going to happen. Also, in order to infer and interpret the kind of activities and the kind of social dynamics that are in these groups. One of the more recent things is what we did last year, which was at ACAI, and there was the whole challenge issued also by things like the Allen AI Institute to tackle exam questions. I mean, one way of measuring progress in AI is like seeing how AI systems perform at well, tasks that would require intelligence if they're performed by humans. Taking exams is, of course, one of these tests. And so they've issued a number of these challenges on like solving mathematical problems, solving also like kind of problems in biology and stuff like that. But what we've done is like we've focused in on another class of problems, which is typically the kind of questions you get in college if you're studying probability. And so you're given like the text in natural language, and then the question is, what is the answer, basically? And again, you can use these probabilistic programming engines to answer that. You first have to map here the kind of language on the kind of intermediate representation that describes what your problem is in declarative terms, and then you have to get a solver to produce the answer. And the solver can be very much on the basis of this probabilistic programming language. So there is a common theme here, and probably Christian showed you this slide already yesterday. There is this learning that you're interested in. It's dealing with uncertainty, and it's reasoning about relational data. There's zillions of formalisms around, and again, Christian has shown this slide, I'm pretty sure of. He probably showed actually a more modern version of that goes further than 10 years ago, because many, many things have happened since. What I do want to stress is that there is like at least two different angles, and I already mentioned that at the start. You've got the probabilistic programming style, which is very much popular in the US with systems like Stan, Church, Edward, Anglican, and so on, basically. And they actually come also from the field of statistical relational learning, but they're kind of more evolving to the interest in programming language theory, also in hardcore machine learning, I would say. And then there is the statistical relational AI. That's maybe more coming from probabilistic graphical models. That's maybe also more coming from a database perspective. What I'm going to present is this problog and this logic programming, which basically fits both representatives, basically. So what do we have in problog as the ingredients? Well, first of all, it's built on Prolog, which is this kind of simple but elegant declarative programming language, where you can list a number of facts, like Anne is stressed, Anne influences Bob, and Bob influences Carl. And then you can write like rules that will allow you to derive further predicates, further facts from the ones that are basically already in your database. So X smokes if X is stressed. That's what the first rule is saying. And the second one is saying, okay, if Y smokes and Y influences X, then X will also smoke, basically. Who is familiar with Prolog? Who is not? Okay, so I'll give you a little bit more time and further examples to get acquainted with that. So in logic programs and in databases, you typically have like one world. From the facts, you can derive, and the rules, you can derive further facts. And typically, you get like one possible world. But if you're dealing with uncertainty, the easiest way to adapt these languages to deal with uncertainty is basically to take facts and associate them with a particular probability. I mean, this is again an example of this principle that if you want to combine two things, you should look at the simplest, non-trivial thing to basically make them identical. And if you look at the basic things in logic, well, that's basically a proposition. It can be true or false. If you look at the basic thing in probability theory, that's a random variable. And so basically what is done here is you basically unify these two things, right? You say my facts, I mean my propositions, they become random variables, right? That's all what we're saying. We take the facts from Prolog and we turn them into random variables. And so basically this is saying Anne is stressed. With probability 80%, that's going to be true. With probability 20%, so 1 minus 80, it's not going to be in. It's going to be false in a sense. And the same for the other ones. And you'll see how, well, that gives already rise to two possible worlds. One where Anne is stressed, the other where and is not stressed, right? And so you'll see that you'll get multiple possible worlds that we can start reasoning with. I'll elaborate on that. And then there is learning. I won't say too much about that because I know that Fabrizio will spend a lot of time on that tomorrow. But there's two ways in which you can learn. First of all, you can learn these parameters from these facts. I mean, if you're not given the parameters, like in a probabilistic graphical model, in a Bayesian network or a hidden Markov model, you can wonder what are the best parameters that explain my data, and that's called parameter learning. The harder task is that you're not just learning these parameters, but that you're also learning the rules, basically. And learning the rules is very much in line with, well, inductive logic programming and the like. So that to start the introduction to probabilistic prologues. And there is actually, as you'll see, I mean, there's many variations on these schemes. There is the so-called distribution semantics, which is basically corresponding to the random graph model. I mean, remember the network that I was showing. Every of the edges that was in with a particular probability or out with a particular probability. And so that's kind of a random graph model. But you can also take, in a graph or a network, you can also take random walks. And so there have been alternative logic programs, so-called stochastic logic programs, that are actually much more like this random walks. You have a random walk semantics in a sense. That's also what is used to some extent in probabilistic grammars, and that's kind of an alternative. I'll briefly touch upon these as well. That's also the framework that people at Carnegie Mellon have used, like William Cohen has devised some of these, and also Steve Muggleton has initiated the original semantics for that. That's the same. So there's lots of, since the fact that David Poole and Taisuke Sato contributed this distribution semantics in the early 90s, there's been a lot of work on that. Many variations have been built. And I'll kind of go through some of the most important ones. I mean, the conceptual changes, of course, I'm going to focus a little bit on the work at Leuven, basically. Like, there have been extensions towards like continuous random variables. There have been extensions toward constraints, towards coping with time and dynamics, towards working with decisions and semi-rings, and I'm gonna talk a little bit about that. That for the introduction. Maybe if there are any questions as we go, I would say just raise your hand and I can try to answer them, right? So we'll go through a number of different steps. I'll focus first of all on the modeling of the modeling tools that probabilistic logic programs provide you with. I'll then show how you can do inference, and I'm sure that again that yesterday you heard that inference is the key problem. Given one of these probabilistic logics, how can you compute conditional probabilities with these logics? And then I'm going to focus in on the dynamics and showing towards the end some of the advanced stuff, also some of the newer stuff. I'm going to talk also about deep problog, which is a kind of very recent and still preliminary combination of deep learning with problog, basically. Okay, so let's start with the beginning. And the kind of standard example that we're typically working with is trying to model this kind of game. And in the game, you have like two urns. They contain colored balls. There are red and green ones and blue ones. And there's also this coin that you have to toss. And we play a game in a sense. We toss the coin and we draw a ball from each of the urns. And then depending on the outcome of the random game, well, you or I win. The rules of the game are that I win if there is a heads and a red ball coming up, or two balls of the same color, basically. And so we can easily model that in Problog. Basically, what you need to do is you need to introduce random variables. And as I said already in the introduction, the key notion of a random variable is like one of these facts. Here, well, heads would be a fact. If it's a biased coin, it could be coming up with probability 40%, right? And so I can write this down as such. With probability 40%, head is going to be true. And with probability 1 minus 40%, head is going to be false. It's not going to be in my database, basically. The balls from the urns are a little bit more complicated. The reason is there are two colors in there. And so what I use to represent this is this kind of ADs, these annotated disjunctions. And basically this statement says for the first urn, the probability that I draw a red one is 0.3, because there are 3 out of 10 that are red. The probability of the second one of blue is like 70%. And I can do the same for the second urn, basically. And these are the annotated disjunctions. They are also the probabilistic choices that I can make, basically. They're all the the basic random variables that I need, because everything else can be derived from that. I mean, I said that I would win the game if these conditions are satisfied, and now I can just rephrase that in Prolog. I can write, okay, I will win. So win, and then this symbol stands for implication. So it says I win if heads is true, comma stands for conjunction. So I win if heads comes up, and color, and then there is an underscore. So I don't care whether it's the first or the second ball, but if one of the balls is red, that condition is also going to be true. So I win basically if heads comes up and the color of one of the balls is red, which is the first rule. And the second rule is basically saying, well, I win if the color of the first ball is C, and that is the same color of the second ball, basically. So that is what is called unification in a sense. So you can easily read these rules. I mean, it's just Prolog. It's almost like a database. It is very, very declarative, and you can really almost straightforwardly read this. If you replace this semicolon dash by if and comma by and, basically, then you're there. Now, what does this kind of now entail? Well, first of all, I said I have defined the probabilistic choices. These are the random, these define my atomic choices. These are the probabilistic variables in a sense, the basic ones. And then there are the consequences that I encode in logic. Now, given such a program, I can ask all the kind of standard questions that you would like to ask to a Bayesian network. I can ask, what is the probability that I will win? I can ask, what is the probability that I will win if I already know that the second ball is going to be green? And I can also ask for what is the most probable world in which winning is true. So the first is like the marginal probability that you're asking for. The second is like the typical question of interest in graphical models. It's conditional probability in the light of the evidence that the second ball is green. And the third one is like this most plausible explanation, this MPE inference that you're trying to do. In order to see how you can answer that and which are the correct answers, it's very instructive to look at the kind of generative process behind these probabilistic databases. And in order to look at how that works, just look at a program and follow me in how to generate possible worlds from that. What we're going to do is we start off with the empty possible world, and we're going to look at how our rules fire in that world. So the first thing that we'll notice okay, there is this probabilistic fact heads. So if I want to sample a possible world, I toss a coin, I mean, here with probability 40%, and suppose it comes up heads. Then I can add heads to my possible world, and I can actually have done the first probabilistic choice. I can look at the second one. There again, I can like sample one of the two outcomes. Suppose I sample red, then I can add that to my possible world, and I know that the probability with which I will get red in there, that's going to be 30%, and I can do the same for the next probabilistic choice, and I get again that I choose green. Green is also going to be there with probability 30%, and then all I have to do is, well, I have these, let's do it again. I had these three basic facts, head, red, and green. And then I have to see which of my rules applies. And I know, okay, it's heads, and at least one of the balls is red. That means that also win will be implied, right? So I add win also to that kind of possible world here. And okay, this is just one possible sample. There is zillions of other samples that I can do. In the second case, you see that I sample tail, so I don't sample heads. You see that I sample red and red, but also in that case, I'm going to win the game because my second rule said that if the color of the two balls is the same, that also in that case, I win the game. And it's clear that you can continue like that with other ones. In the last case, winning is not true because neither are the balls of the same color, or there is no head in there. So in that case, winning is not part of the possible world. If I do this systematically, I get like 12 possible worlds, and you see that I also get all these probabilities associated to them. And that basically is defining my basic probability distribution. Every possible world has a probability associated to that, and the sum of all these probabilities is equal to 1, basically. Yes?
So my question is, when constructing a worlds for these probabilistic specifications, we mentioned, for instance, the first turn, okay, this is the product of red and this is the product of blue, but could we also say something like, instead of this, like explicitly restating what is there itself, the first term only has blue or red, and the product of picking up a red ball is, let's say, 0.3. Would it be able to infer that 0.7 and the other instead of exhaustively stating all these things, just having a more general rule like.
Yeah, here in Problog, that would be harder to do. I mean, in Problog, that would be harder to do. In other logics, this is easier, but that has disadvantages as well. I mean, here the advantage is that you get precise possible worlds, and every possible world has its known probability. In other cases, you have to make extra assumptions, like in Markov logic, where you make the maximum entropy assumption that maybe, okay, you don't know whether it's red or green, but then you know that the sum of the probability of red and green is X, but then you have some way to kind of spread that over these two possible worlds in a sense. And so you need to make extra assumptions. Typically, one then makes the assumption that, okay, things are almost equally likely, but I guess Marco and Srira may be talking a bit more about that kind of scheme. Yeah.
Does this language also allow to label these implication rules of probabilities?
Yes. Well, in a sense, what you do is, that's in a sense what you do with the second. I'll give examples of that. I'll give examples of that. So, I mean, this is just like the basics, so bear with me. I'll give some further examples. Slideshows. Okay, now I can just use this to look at all these probabilities. What's the most likely world? Well, I can, where winning is true, I can basically look at all my worlds and take the one, well, that is has maximal probability, and then I'll come up with the one in the bottom right. I can look at most likely world where column where the second ball is not blue, and again I can find one. The more interesting questions are typically this marginal and certainly the conditional probability. What's the probability of winning? Well, I just look at all the walls in which winning occurs, and I sum up their probabilities. And if we computed this correctly, that should be 0.56. We can then look at conditional probabilities. What's the probability that I win, given that the color of the second ball is green? Well, in that case, I first look at the ones having second ball green, and that's like the middle row. And of that one, only the left one, that's the orange one, is giving me a win. And so I can compute the conditional probability just using the standard definition of conditional probability here, basically. And so what you get is like this, what is called the distribution semantics. In a little bit more formal way, you've got a query here, your facts, that's F. These are the probabilistic facts. R are the prolog rules. And then you basically say, in order to compute the marginal probability of a query, I need to sum over all the possible walls where that query is going to be true. And I'm going to look at all the, at the subsets of the probabilistic facts that make actually the query true together with my rule. And every of these possible walls has the probability that is listed there. I mean, you've seen that also in the case when I was doing this generative process. I always looked at the probability of the facts that are in, and I multiplied by the probability of 1 minus the facts that were out, and that's basically the second component. So that's a little bit more formal, and Sato and Poole have shown that all of this is pretty well defined. You can also view, and that is answering your question, you can also use this in a little variation. That's actually the LPADS and CP logic introduced by Joost Vennekes, about 15 years ago as well. And the interesting thing is that you can model this generative process in a kind of tree process, where in the, again, you'll see that for this program, it's very similar to before. You have John always throws. Mary throws only 50% of the time. If Mary throws, then the window will break with probability 80%. And then with probability 1 minus 80, nothing will happen, right? So you don't specify the alternative. And then if John throws, the window will break with probability 60%. And so then you can ask, what is the probability that you will break? And here is the full generative process that is modeled. Initially, it's the empty possible world. John always throws, so that's the certainty. So just below there, you've got, maybe I should take the pointer. Just below there, you've got John throws. And then, okay, if John throws, well, the window can break with probability 60%, or it doesn't break with probability 40%. Here, I can have Mary throw with probability 50%, or not throw with this probability. And so you can build up this whole kind of generation tree if you want, and then you can look at the bottom in which of the leaves will all be the possible walls, in which of these leaves breaking will occur. And Well, the probability of this world is just the product of all these probabilities here. So that should be this product. This should be that product. So again, you can kind of sum all of that up, basically. Okay. One of the interesting things about this view is that it's regardless of the order of applying the rules, you will always end up with the same result. So it's kind of pretty well defined. Another reason why I was showing this is that you can also use this to define a variation, which is called DC for distributional clauses. And the variation is this. While before we had like a condition that would say, well, if this condition holds, then you have one of a number of alternatives with particular probabilities. Like, okay, if John throws, the window breaks with probability 80%. Now we do something different. We say if this condition holds, if there is an object of type glass, then the length of the object will be distributed according to a continuous distribution to a Gaussian basically with mean and variance. And the way to view this is that if you look at the generative process in the previous slide, you would always have a finite number of alternatives. But if I here say, well, draw from a Gaussian, then I've got an infinite number of possible outcomes, basically, right? And so you can use the same kind of principle to define what are the possible walls with these continuous distributions. And that is what we've been using in a more robotics kind of action and activity setting, where continuous distributions really matter, because if you're referring to objects, well, they are at particular locations, and that's like in terms of coordinates that you typically have these, and so you need to be able to reason with that. Also, in this kind of settings, you want that the length of the object takes on real values, and then you can reason with that very much like you would reason with the other variables. Here you say, well, a bottom object is stackable on top, well, the top object is stackable on top of a bottom object if the length of the bottom object is larger than the length of the top object, and similarly for the width of the object. So you see that you define very much in the same fashion the kind of rules, and also the kind of random variables, and you can reason with these as you would typically like to do. This semantics is very similar to what you find in probabilistic databases. There's a whole body of work that is relying on that. There is the work of Dan Suchu and his collaborators who have studied a lot of the theoretical properties about inference and reasoning with these. But in SQL, what you would be doing is you would have tables, and you would have like this SQL queries, like here. In a probabilistic database, but again, it's the same in a deterministic database, you would get one possible walls. In a probabilistic database, you would allow every of the tuples to get a particular probability. It's with probability 87 that Anne was born in London, Bob in York, probability 95%, and so on, basically. And so, again, you can capture uncertainty about your tuples, and you can reason very much in the same spirit as we did with problog. You can actually directly map this probabilistic database representation onto problog. You get a probabilistic data log, if you like, for the people that are interested in that. And it's very much the same semantics. It's very much the same kind of semantics. It's this, to some extent, that is used also in NEL, at least in the spirit. Yes? I didn't get that, sorry.
Is there some harm related to the angle of functional dependencies when you have a probabilistic.
To functional?
Functional dependencies when you say, for instance, that when you have the name and the
yes.
nickname, the value of some set of attributes implies the value
yes.
of others.
Yes, so you can actually, I'm going to show it in context of Problog, but you can use constraints in these probabilistic databases, in these probabilistic logics, and functional dependencies would be one of these in a sense. So I'll show how that works. But again, I mean, the idea is that you can query this. People have done a lot of theory about inference and about interesting query mechanisms for these databases. Let me go through that. You can also model dynamic processes like hidden Markov models or Markov models with this kind of setting. And there you see already the power of programming languages to some extent. For instance, in a Markov process, at day 0, you might have sun or rain with a particular probability. And then if today it is sunny, then you could have two rules. First of which says that if today is sunny, sorry, it says rain. If today is sunny, then tomorrow, so that's at time t-1, this is at time t, tomorrow it's going to be rainy with probability 40%, or sunny with probability 60%. That's capturing the transitions on top. And then you can have like another one that captures the transitions at the bottom. Again, you can show that all of this is well defined, and you can easily model hidden Markov models and stuff like that. So very much what applies in the general case, very much what I've said before does apply in this kind of case. I don't want to spend too much time on this. There are more interesting things to look at. Also, that I think will be an example that will be. Let me rather summarize the basis of what I've said. You got probabilistic choices and their consequences in Problog. It generates a probability distribution over possible walls. And then you can look at the kind of questions to answer. Of course, doing this generative process is not what you want to do. Because, well, it's clear that even for the most tiny databases, that will be very, very hard to do and will run into combinatorial problems. So the thing to do here is basically to look at alternative inference methods. And there is like some kind of assumptions that you can make. Some systems, like the earliest system that was doing this kind of setting was Prism. And basically what this is doing is the assumption is that only one rule can fire at the same time. And we'll see that this simplifies the inference to a large degree. I'll be going for that's the Prism, and I think Fabrizio will be talking more about Prism tomorrow, so I won't go into the details here. Let me rather skip that part for now and give you a little flavor. I mean, this was the distribution semantics, the kind of possible wall semantic that you have in Problog, that you have in Pita, that you have in some of the other, in Cplint, that you have in this kind of systems. There's also the other view, which is more like the random walk view, that I basically want to mention very briefly. That's the stochastic logic programming view, where you work more like in probabilistic grammars, essentially. And what these are is like you have the rules of a grammar here, and the rules are annotated again with probabilities, but there is a big difference with the way that we annotated the probabilities in Problog. The difference is that if you look at any of the non-terminals, like article here, that the sum of the probability is equal to 1, right? So the sum of the probability is equal to 1. Also for a verb phrase, you see that the sum of the probability is equal to 1. And again, this defines a probability distribution over possible parse trees, because yeah, I mean, if I start with sentence, well, with probability 1, I'm going to get a noun phrase and a verb phrase. Then the noun phrase is going with probability 1 in article noun. And I can basically look at what probability I get here for the turtle sleeps. The probability that I get is taking the product of all the probabilities of the rules that I have applied, basically, right? So this grammar generates that sentence with this particular probability. And so you can formalize that. It could be that some grammars have more than one parse tree for a particular sentence, right? It could be that there are 2 parse trees for this, and then the probability of that sentence being generated in the grammar is like the sum of the probabilities of all the parse trees, essentially. That makes a lot of sense to have this kind of probability here. Now, the interesting thing is that if you look at PCFGs, then the parse trees, they always succeed. What this means is that if I take a rule like this one, like S rewrites into T and Q, and T rewrites into R and U, that I can always rewrite it in this form, right? If you do proofs in Prolog or in first-order logic, it can be that, well, there are arguments to that, and that unification makes that this fails, actually. Here is a little example. This is what is called a definite clause grammar, and it's a probabilistic one. You see what has changed is that my non-terminals, they've been given arguments. And for instance, here it says that a sentence, there should be a number agreement between the noun phrase and the verb phrase. I mean, they should either be both in singular or in plural form. And the same holds for the article. And then you see that, well, Z can act as an article for the singular form with probability 20%, plural with 20%. And so at first sight, it seems that you can do exactly the kind of derivations that we were doing just a minute ago. And that is true. I mean, if you've got a parse tree that is successful, you can again compute the probability. And this is very much what stochastic logic programming is doing. There's only one caveat, and the caveat is basically that some proofs might now fail, basically. You see here, I can write that one, but the turtle sleeps, but I can no longer parse A turtles sleeps, because, well, A and turtles, this is singular, and this is plural form, so there will be no parse tree that allows you to parse that one. And so here you lose some probability mass, basically. Some parse trees that you were able to obtain before in the kind of propositional case, in the case where you were not using unification, in the case where you were not using this logical mechanism during your derivations, that meant that all proofs always succeed. You could always rewrite. Here, there are cases where you cannot longer rewrite. I mean, you will not be able to find that article singular, which you would need for A, matches with noun plural, basically. That would not match because number would be singular here, and there it would be plural, so you would fail your derivation. And so you would lose some probability mass, basically. And that is actually what you get in this stochastic logic programs, which you see here. I mean, this is just the same, this is just a direct mapping of this probabilistic definite clause grammar onto, well, these stochastic logic programs where you use Prolog notation rather than this kind of notation. This is a lot more intuitive, though, but a bit more restricted as well. Now, the interesting thing is that you have to correct for that. If you lose some probability mass, then, well, the sum of the probabilities of all the sentences will no longer be equal to 1. And so you have to normalize and you have to correct for that. And that is what is done in the semantics of this stochastic logic programming languages. It is this idea that is also used in a lot of the applications of William Cohen and Tom Mitchell and William Yang at CMU. And they've been doing a lot of cool stuff. They've been working on web-based data, on NEL data, and they've come up with a variation on this idea of the stochastic logic programs, where you write down Prolog programs and you label them with a number of features, basically. And you can then automatically train them. And they've used this approach, this ProPPR, to do a lot of applications in link prediction, like predicting whether there are missing links in a network, and things like that, also doing classification with pretty good results. There have been a series of papers on that topic. And essentially the idea of this ProPPR is going back to this idea of probabilistic definite clause grammars, where you, in a sense, do a random walk rather than you do a random walk rather than working with random graphs, as in the Problock thing. I'm leaving in the slides so that you can check for them later. The last thing that I want to say of modeling so far is that I was talking about these other programming languages that are not logic-based and that are also using probabilities and probabilistic primitives in order to specify models and to do inference. There have been a whole series of them. Avi Pfeffer is one of the first who have been doing that. And then today, people are using things like Stan, Edward, and Anglican, which are pretty powerful tools in a pure machine learning setting. I'm not going to illustrate these, but rather I'm going to look at a functional language called Church, which is, well, relatively easy to explain in the context that we're working with. So rather than using logic, what they use is functional programming. And a lot of these probabilistic programming languages are actually built on ideas of being functional. In functional programming, you can define things like this, plus 5. I mean, I've got a function of an argument, and I will basically return that argument plus 5. And then I can map, I can apply that argument, I can apply that function to this list, basically. And what I would get back is like 5, what I would get back is 5 plus 1, which is 6, 7, and 8 then as an argument. Now, the idea here is that rather than looking at possible walls, you look at possible executions. And in a normal functional program, there is, for every result, there is like typically one possible execution that you will get. If you inject random primitives, you can actually make the program choose between one or the other of the execution trace. And here you see like one way of injecting that. What they've injected is like a flip. And that flip is very much like the fact that we had in Problock. You can flip a coin with probability 60%, it's gonna be true. With probability 40%, it's gonna be false. And so what you say here is, if I flip and it's true, you take the first branch and you're adding 5 to your argument. In the case that flip fails, you just return the argument. And then you'll see that you get many different execution traces for this kind of function. Maybe we can have a look at that. The Church result, and I didn't illustrate it on lists of size 3 because that's even a bit more complicated, but I can look at what happens if I do this random plus 5 at 1 and 2, well, if the flip fails twice, I'll basically get the same result. I mean, the input will be equal to the output with this probability. And you see if the first one fails, but the second one succeeds, I'll get this probability. And so you see that you get a kind of, over all the execution traces, you get a particular probability, basically. If you would map that naively in Problog, you would get this kind of program. This is just list manipulation in Prolog. If you're not familiar with that, it's not so important. But here you basically define this plus 5, right? This here basically you say, well, with probability 60%, you'll get M, so that's the thing plus 5, and here you'll just get the same number, basically. Now, if you apply that, the Problog result is gonna be like that as well. But it's interesting. So if you naively apply that, you'll get the same kind of result here as for Problog. Now, the interesting thing happens if you apply that Problog program to 1-1. And the reason that it's interesting is that there is something going on which is called memoization in Problog. Whenever you decide upon a possible world, and in that possible world, you choose like whether you get this branch or you get that branch, then whenever you need P5 again on the same values, like here you do it once on the first argument, and say that you get the false branch, right? Then that will be memorized, and whenever you get one again, and you need to look up what you got, you'll get that same value again. And so if you apply the Problog program onto 1-1, the thing that you will be getting is 4 possible outcomes, but the probabilities will be quite different from the probabilities that you would get with the church program. And the reason is that there is this difference in what is called memoization. In church, whenever you encounter flip, you will flip the coin again. In Problog, you will look, oh, did I flip that coin already before? And if I did, I will look it up what the value was and I will use that. And that means that I get a different probability distribution. To get the same kind of thing in Problog, you can get around it, but in order to do that, you need to add basically an identifier of the coin. That's basically that whenever you flip, you'll flip a new coin in the sense that you add like this identifier. It's a bit technical, but it shows that there are some differences in semantics that can sometimes be a little bit tricky. Okay, but given that, you can very easily, and that's actually an interesting exercise to do, you can try to model the gambling game in Problog, which we've seen, but you can see whether that gambling game in Problog can be mapped easily onto church, and indeed you can do that. The only tricky thing is that you have to do memoization in church, basically, because whenever you flipped heads, well, heads is gonna be the same. I mean, that's the Problog semantics. So in church, you have to add this memoization to simulate the Problog setting, whereas in Problog, you have to add the identifier to get the church setting, in a sense. Okay, and then you can reason about this. You can do the same kind of queries. You can ask, okay, what's the probability that I will win? You can add evidence, and you can do similar things. Let me conclude this part on modeling by giving a little bit of a summary of the different paradigms. I've mentioned 3 key languages. especially Problog, which is based on Prolog. It gives you a distribution over possible walls. In Church, you get a distribution over possible execution traces, answers. It's based on lambda functions. It's based on scheme, actually. And yeah, the other thing is that there is this memorization that you get in Problog, but you do not get in Church. But you can declare it. You can simulate it here as well. And Prism is making a simplification with regard to Problog, in the sense that it assumes that the derivations are mutually exclusive. More about that when I talk about inference. Let me check how long I've been talking. Okay, maybe I'll talk a little bit about inference now. Then we can take a break, and then I'll go to some of the applications and the more advanced stuff later on. Are there any questions still about the modeling part, about these different languages and stuff like that? Maybe I should also stress that if you go to the WASP tutorial, the one that's on the first slide, basically, if you look for WASP, W-A-S-P, Problog, you'll find my slides, and you'll also find exercises. And there is like a couple of exercises that you might want to make. Certainly, I guess the first and the second would be good to make, unless Marco is planning. Yes. So if you want to get your hands on with Problog, it would be good to make certainly the first, maybe also the second exercise. There's also one about learning a bit later, and there's two more advanced ones. So 3 and 5 are probably much more advanced. The nice thing about Problog is that you can really get into the, there's an online interface where you can type in Problog programs, and you can really test out what the effects are. So if some of the concepts you want to check for yourself, I'd really encourage you to go to the Problog website, there's also an online tutorial with loads of examples that you can take. And there's a couple of exercises on this WASP, on this WASP tutorial. You can also find the solutions there. Should you have difficulties, don't hesitate to ask me later. This week I'll be around most of the week. Okay, if there's no questions about that, let me go to inference and reasoning. You'll see that most of the work, both in probabilistic programming and in star AI, is on inference. The reason is very simple. It is a very hard problem to compute these probabilities. It is Sharpie complete or hash P complete. I'll try to say what that means. And that also even holds for Bayesian networks. Also, inference and probabilistic graphical models is like very, very hard. It's even hard to approximate. And that actually has as an effect that most of the work is really making inference tractable. It's clear that the generative process that I illustrated to get you the possible walls, you don't want to do that. I mean, if you have like a couple of tens or hundreds or thousands of facts, you don't want to pursue that generative process because it will simply explode. So the question is how to answer queries in this. This is definitely going to be infeasible, the generative process, so you'll have to do better than that. And there's typically two components, two solutions to this. On the one hand, there is a logical component, and on the other hand, there is a probabilistic component. And basically, the two styles of reasoning are being applied. There is, at the level of logic, there's two things that you can do. You can, first of all, if you have a logic, you can compute proofs. Or two, you can look at a model theoretic perspective, and you can look at which are the possible models, the possible walls, and you can compute with that. And that is, I mean, what you've also seen yesterday, that is connected to weighted model counting as well. And then you can do probabilistic inference. which you can also reduce to some kind of logic using knowledge compilation techniques. But people have also used things like variable elimination, belief propagation, and so on. And then there is the advanced inference, which is lifted inference. Maybe I'll also still say a little bit about that towards the end. Let me first illustrate what the problem is. If you look at a proof theoretical perspective, if you look at this program, then basically you can build proofs for that. And so here you've got these facts and you've got these rules again. The rule says if you smoke if you're stressed, or you smoke if you're influenced by somebody who smokes. So if I want to check whether Carl smokes, I can use the first rule, and I say, is it the case that Carl is stressed, right? Carl is stressed, it's not amongst my facts. So that proof will fail, basically, right? That proof fails. The second thing I can do is there's somebody who influences Carl and who smokes, right? I apply the second rule. Then I come here. Okay, I've got two conditions now. I have to prove this and that. Is there somebody who influences Carl? Yes, there is. If I substitute Bob for Y, then, okay, Carl is influenced by somebody, and all I need to prove is smokes. Well, this Y equals to Bob propagates, I get smokes of Bob here. So I have again, now I need to prove smokes Bob. I got again these two possibilities. Is Bob stressed? No, he's not. I got the other possibility. Okay, here is there somebody who influences Bob? Yes, Anne does. And I got the same process. But this time, okay, Anne is stressed, and I basically have a proof ending in like the empty condition, the empty goal, if you want. And so I've got a first proof, and along that proof, I can basically gather all the facts that I've used in that proof, basically. If I got a problem program, the only thing that will change superficially is that there will be probabilities associated to that. And so I can compute the probability of that proof. I mean, it's very much like what I have in the context-free grammar, almost, except that here, well, I could add further facts for influence so that the sum for influence is larger than 1, basically. But the probability of that proof is just the product is equal to that. So far, so good. And you're tempted to say that the probability that Carl smokes is equal to that. And in this case, it is correct. Let's now, however, add a second fact. Bob being stressed. If I add a second fact, then, well, I get a second proof here, basically, right? I got the original proof that remains, I got a second proof, and at this stage, it is pretty tempting to say, well, let's look at the probability of that proof, look at the probability of this proof, simply add them up, and that's going to give me the probability of smokes. Is this correct? Yes or no? No, it's not correct, and the reason is that these conditions are not disjoint, right? I mean, if I add up two probabilities, I need to make sure that, well, these conditions and these conditions, that they are mutually exclusive. And they are not, basically, right? The proofs overlap. You can see it easily here. These are the possible values that I get for, well, the first proof. And these are the possible values I get for the second proof, basically. And so you see, if I take the probability of the first proof, and I sum it up with the probability of the second proof, well, I've counted this guy twice. And in that case, I've made a mistake because I should actually subtract also that probability. Now, you might think that at this case, this is not so much problematic, but it's this that basically causes all the trouble with inference, basically. It's also this that is avoided by this language prism that Fabrizio will talk in more detail about tomorrow. In Prism, it is assumed that you don't need to, well, that whenever you've got two proofs, that they're always disjoint. And that simplifies the problem to a large extent, because all what you need to do is generate the proofs and add up their probabilities. Here, you need to do an extra step. You have to disjoin them. And that's actually a hard problem. The solution that we are taking is one of knowledge compilation. Let me see, should I? Well, you can actually show that it's, the thing you can show is that evaluating in general these kind of queries is computationally very hard. And there are also cases where it's easy, but these cases are pretty limited. Here you see like a simple program. It's again distress and influenced. And you see that you get these kind of proofs. If you look at the tree that you get here, I mean, these are the ones for stress, basically. These are our random variables. You see the ones for influence. And this is a pretty nice structure. The reason that it is a pretty nice structure is that none of these facts occurs multiple times in this proof tree. And in this case, it is actually easy to compute the probability. You can show that these two rules will basically apply and that they are sufficient to compute the probability of Q1 being true. This is in a much more general case, and it's polynomial. However, I mean, if I now add this extra condition on Y, and okay, I also add like probabilistic stuff here, then I get something which is no longer a proof structure. Well, it is a proof structure. Sorry, it's a bit annoying with these. I mean, these are all the proofs that I get. Now, if I look at their structure, I get something like that. And that's no longer a tree structure. And at that stage, I really need to disjoin them, and I get into all kinds of problems. And this is what shows that it's really computationally hard. It's just an indication. People like Dan Suchu have done seminal work on like analyzing the complexity, on like showing this kind of big property that if you have a union of queries, that it's either polynomial in the database size or hash pre-complete in a sense. Most of the problems that you'll get with are actually in this region of the search space. And the distinction is really, I mean, this is fine. This you can compute efficiently, but as soon as you add an extra condition on Y, the game is over, basically. Then it explodes. If you're interested in this kind of stuff, I would say look at that Suchu's work. Look also at work by Guy van den Broek, who very nicely explained this. It's this that also gives rise to all the trouble, basically. But let's look a little bit at how you can do that now in practice. There is this disjoint sum problem, and in the disjoint sum problem, the solution that we typically take is to look at the two proofs that we have, right? We've got these two proofs, and then we kind of try to compile that into a structure that allows us to do the efficient inference, that allows to avoid that problem. And this is called knowledge compilation. There is several forms to which you can compile. You can compile to binary decision diagrams. There's actually a whole literature on knowledge compilation. Knowledge compilation is just about taking Boolean formulas and compiling into some form that allows efficient inference. And that can be of different types. There's very different operations you can do on Booleans. Maybe you can take two Booleans, you can look at, are they identical? I mean, are they equivalent in a sense? That would be like one type of operation. Other types of operations are like this probabilistic inference you want to do. And for probabilistic inference, well, first of all, you can use these BDDs. People today use already more advanced structures like SDDs. People have also used DDNNFs, and these are all like special forms that allow you to do to solve this disjoint sum problem in a kind of efficient manner. Of course, the step in going from your logical formula towards this form, that is the expensive step. But the idea is that you take your program, you compile it once, and then you can actually answer a lot of questions on that on that compiled structure efficiently. And that's also what is used and what is state of the art in Bayesian networks. People at UCLA like Adam Darwish, Arthur Choice, and others, they've basically done a lot of work on this knowledge compilation. They've built libraries that will take formula in logical form and will compile it to efficient data structures that allow some of these efficient inference. They've also won a lot of the inference competitions in graphical models with these tools. So this is really state of the art. Let me just illustrate on using the simplest diagram how this works or what the idea is. I got a logical formula here, X or Y or Z, and I can check all the well, possible assignments here. I can look at X, Y, Z, what are the possibilities for assigning. I can look at which ones are actually true, and okay, for X, Y, or Z, well, it's just the first one that is gonna be false, basically. And I can also represent that in a kind of diagram. And BDDs have the property that at the first level, at every level, you have only one variable. So first, I choose X, then I choose Y, then I choose Z, and I've got always a false and a true branch. So the dashed line is X going, X being 0. The straight line is X being 1. And I can kind of recursively do that. And then I see that, okay, I get, as a result of that function X, Y, Z, X, Y, or Z, I get basically always true here. And here I got a false, basically. Now this is kind of a non-compact representation of that function. And knowledge compilation is all about making this kind of representations much more compact. And in order to make that much more compact, I can actually notice that some of these branches are actually the same. Here, whether I got a 0 for Z or a 1 for Z, I get the same result. Same here and same here, basically. So what I can do is actually, I can merge that. But before merging that, what I will do, I will just take two nodes, the 0 and the 1 node. That's the first step. And then you see here, you see it even better, that no matter whether I take the left or the right branch, I get, for Z, I get a 1, same here, same there. And so these are kind of unnecessary. So I can delete them. Now I get, well, this phenomenon here, no matter whether I take Y or Y equal to 0 or 1, I can also delete that. And so I get a structure like that. And this allows me now to compute efficiently the probabilities and to kind of disjoin it, right? What I need to do is I take first the true branch, X, and then I say or, well, I take not X and Y, right? And of course, X and not X or Y, they are disjoint. I mean, they don't overlap. right? This is the orange part. And then I can take the last branch, which is not X, not Y, and Z, and that's going to give me the last branch. And so you see that here, I've basically kind of disjoint this expression into components for which I could add the probabilities. I can now add the probability of X to the probability of not X and Y, the probability of this and that, and so I can efficiently compute that probability from these kind of structures. And you can do that then again on the kind of settings that we had with influencing Bob and Anna and Bob and smoking and stuff like that. I can do that on the proofs that I originally have and compute the original probability that I wanted basically from this. People will typically do it bottom up, computing that probability. I just took these two proofs, compiled them into the circuit, and then I know that I can basically go up here. These are the probabilities that Anne smokes, the probability that Anne doesn't smoke, influences Anne Bob false, influences Anne Bob true. And what I now can do is like, I can kind of propagate this upwards, and the probability of stressed Anne is going to be 0.2 times 0 plus 0.8 times 1. That's this one. Then I've got the value for this node, and I can look at the probability of this, which is 0.4 times 0 plus 0.6 times what I had here. And I can simply propagate that upwards, and upwards I'll get the ultimate probability that I wanted, which is the probability that C was smoking, Carl was smoking, basically. Right. Okay, so that's the idea for knowledge compilation. Yeah, I was also saying that there is two ways in which we can do this. I showed you now the proving way, that if you have a query, you prove in all possible ways how you end up, how you can prove the query. Then you get like the disjunction of these proofs, you compile, and you do this. In logic programming, you also have the other way, which is that you ground out something. And that's the model theoretic way. Let me just illustrate that on another slide. Right. Let me illustrate it on this one. If I have this theory, what I can basically do is I can look at all ground instances of this theory, right? I can substitute X by all possibilities that I have here, and I can see what are the relevant ones in order to prove call. And I'll get a couple of sentences like this. And then I can map that onto another formula, which I can put into CNF form, and I can start from that. That's going to be a reduction to weighted model counting, the kind of technique that Weishak was talking about. I'm not going to go into further details about this at this stage. I think I'm going to have a break. Are there any questions right now? Okay, if not, then afterwards we're going to continue with the more advanced stuff, which is the dynamics, the robotics, the deep learning, and all of that.